So let's start with a little recap. We managed to rewrite Maxwell's equations in terms of this antisymmetric tensor and a fork current. And then we argued that these are invariant under a certain symmetry, right? And the symmetry was x mu is lambda mu nu x nu. And we have to introduce upstairs and downstairs indices. That was really forced on us by the form of Maxwell's equations. Okay, and you can kind of see that because when you write out the Maxwell equations, one of them involves this. So you've got something with a downstairs index. You have to define the f with the upstairs index because this is defined with the downstairs index. But on the other hand, the other equation involved epsilon. And this epsilon is defined with upstairs indices, epsilon 0, 1, 2, 3. And now the f has to have a downstairs index. So somehow you've got to have a way of relating upstairs to downstairs, and that's why you need the eta. Okay, so it comes in a sort of slightly obscure route that you see in order to write the Maxwell's equations. And if you try to do it without the eta, you will fail. Okay. So, and maybe, a consequence of all this is that when you write the wave equation, that's kind of how I motivated it. When you write the wave equation, you've got to have a minus sign in the time direction, right? And so we took these equations and we derived an equation like this. And you certainly need an eta to write the wave equation. Okay? You need that minus sign. So, so we had to introduce this eta, and the eta is used to raise and lower indices. This, d by dx prime mu transforms with the inverse matrix. So we introduced all these structures, and I'll do a little bit more of this today. What I want to do is to show you another famous law of electric. Well, let me just summarize. So then we constructed a momentum. We know that energy and momentum are very fundamental concepts. These were kind of known from Maxwell's work and following. What is the energy in an electromagnetic field? What is the momentum? I gave you an expression yesterday for P mu in terms of F mu nu. Essentially, P mu turned out to, if we have an electromagnetic wave where, let's say, the electric field is propagating along at the speed of light, some pulse of electric field, then we can combine the energy and the momentum of the wave into a 4-vector, and I showed you that this px is equal to E over c. Okay, and that's obviously with a wave going in the x direction. If I just rotate the wave in any direction, I'm going to get mod p equals E over c in general. Okay, so this was known that you have electromagnetic waves, they carry energy, they carry momentum, and this is the relationship between the energy and the momentum of electromagnetic waves. A completely classical result. You didn't need any relativity to derive it, and that was known. So the first thing I'm going to do is to show you how Einstein argued that this formula on its own for electromagnetic waves gave rise to E equals mc squared. Okay, in a very simple physical argument. And actually, the first time around, he made it too complicated, even though it was only a 3-page paper. And so the second time around, 1947, he got the argument a little bit clearer, and that's the version I'll show you today. It's described in Tony Z's book. Even that argument isn't really the right argument. Okay, it's a very clever argument. It's not the right argument. The right argument rests on Noether's theorem, as I explained yesterday, and so that's what we're going to we'll do in these 2 lectures. We'll extend the electrodynamics a little bit more, and then we'll be ready to discuss Noether's theorem and energy and so on. Okay, so Einstein's argument, 1905. But then improved in 1947. So Einstein said the following. Let's just believe that we know that electromagnetic waves carry energy and momentum, right? And let's just take on faith that energy and momentum are conserved in the world, right? Without explanation. But there is something called energy and momentum, and if I emit some energy, I've got to ensure energy is conserved, and likewise for momentum. Okay? So consider the following situation. I've got some massive particle of mass m, and then after a while, this represents time. After a while, the massive particle emits 2 photons. It changes into another particle of mass little m, and it emits 2 photons. This symbol is for a photon, gamma. It's not a Greek letter. Let me maybe write it photon so we don't confuse it. But I do call it E gamma. Yeah, that's a bit confusing. The gamma is not an index. We call it gamma. Gamma is used for a photon. Okay? And here we have another photon. And by symmetry, let's just assume this little particle emits 2. There's nothing to distinguish between them. And so this is the same energy. Okay, so the point is we want this particle, after emission, to be at rest. So it just sits there. Bang, out go 2 photons, the particle's at rest. Fine. Now, it's very plausible from this picture that the energy associated with this particle, right? I mean, obviously, I've emitted some energy. So I must lose the energy of the product particle has to be related to the energy of the initial particle by this formula. Okay? That's just energy conservation. We still don't yet know what the energy is as a function of m. In fact, that's what we want to find out. We want to derive E equals mc squared. So that's the first point. So we'll work in a frame where m and m are at rest. Okay, so things look very obvious in that frame. Now, actually, I'm going to call this frame O prime. Okay, so it's because I'm now going to work in a frame where m is moving. And so O prime is the frame of this particle. Okay? And so actually this is prime, and these are primes. Okay, so now we're going to transform. We're going to go to a frame where m is moving with velocity v. Okay, so that will be a frame O. So we'll have a space-time picture that this is O, and this is O prime, right? T prime, CT prime, X prime. So obviously, according to O, O prime is moving. The particle capital M is going to be moving along this axis in just through time, CT prime. The position will remain fixed. Okay, so in this, what we're going to do is assume momentum conservation. In O. Okay, so in O, the particle's got some momentum. Not just energy, actually has some momentum. So we have this situation. M is moving along. M is moving along with some velocity v. And then it emits 2 photons. These are going to be going now in the forward direction. These are E gamma, and this is M, little m. And little m must also be moving at velocity v, right? After all, in this frame, little m was stationary. So if big M is moving to the right, so I just look at this. They're stationary, and now I'm moving. Clearly, they're both moving at the same velocity. So they're both going along with v. And clearly, the photons are not directed vertically because I'm going this way, so the photons must be coming towards me. Have some component of their velocity towards me. Now, what's the relationship between this energy and that energy? Well, it's not hard to see. You can do it with a Lorenz transformation. If you believe energy is a 4-vector, right, then in this frame, my 4 momentum of a photon is so the pz is, okay, so this photon has the following 4 momentum, right? And so if I do my Lorenz transformation, just think of this component as CT prime, and this is X prime. And now I want to go, and this is P prime, of course. It's P in the primed frame. So let's go to P mu in O's frame. And we know what we do there. We write CT is gamma CT prime plus V x plus V over C squared x. Or is it V over C? V over C x. X prime. Right? That was just the Lorentz transformation we did last time. To go from this frame to that frame. So clearly, this 4-vector, I just take the time component here, and what I get here is gamma E gamma prime over C. And then because there's no X component, sorry, this is X prime. This is Z prime, right? Because X prime is 0, there's no X component of the momentum. That's all I get. And so on, other components. So obviously it's true that E gamma is E gamma prime times gamma. Okay, kind of makes sense. If the photon is going up here, and now I move towards it, I'm going to see the photon coming a little bit towards me, right? And why does it have a higher energy? Well, that's sort of obvious, because if you think of the photon as having a wavelength, imagine it's coming directly towards me, and I move towards it. Well, I'm going to see the peaks closer together, right? The photon's coming towards me. I'm going to receive the peaks at a shorter time interval. So that means the frequency is higher, the wavelength is shorter, and we know that means the energy is higher. So that's the gamma factor. But then the beauty of this Einstein argument is all you really need to know about this quantity is that it's of order 1 plus something times v squared, right? So gamma equals, of course, root 1 minus v squared over c squared, but it's basically 1 plus or half v squared over c squared. And if v is small, this is small, right? That's order v over c squared. Okay, so what we can infer from this is that E gamma is approximately E gamma prime, right, to order v squared. And so now we know E gamma prime. And because we know E gamma prime, in terms of E gamma, we know the momentum. So now we can write down momentum conservation. mv, so total momentum of this guy, is little mv, and then plus. So we now think about the momentum carried by these photons. So there are two of them, two photons. This corresponds to a momentum of E gamma over c. Okay, and now we want to use momentum conservation, but we have to take the component in the x direction, right? This is the x component of momentum. So the x component of this p gamma is E gamma over c times cos theta, where theta is this angle. Sorry, theta is not that angle. Theta is this angle. Right? So the x component of this momentum is along there.
They don't know.
Sorry? Oh, so I had it right. I'm sorry. I'm sorry. Thank you. Sorry, I had it right. Oh, wait a minute. Sorry. No, I'm wrong. Yes, sorry. So theta is nearly pi over 2. Yes, that's right. Sorry. So let me redefine theta to be this one and write this as a sine. Okay, now are we happy? And theta is small. If this velocity is small, theta is small. Okay, so what is sine theta? Well, sine theta is just v over c. If v is much less than c. Okay, so why is that? Well, basically this photon is now so I have this picture where the photon is going here. This component of the photon is v. This component is c. And so the angle is, so sine theta is approximately v over c. Okay, so you just take the sum of the two velocities. Okay, and if this velocity is small, that's absolutely fine. Just add the two velocities. You see, the thing you might worry about is if I add two velocities and ask what is the net velocity, it looks like it's square root c squared plus v squared, which looks bigger than 1, right? But actually, the error is v squared. And so you're OK. To order v squared, you can simply add the velocities. OK? So sine theta is v over c. So if we believe that, then this formula, sine theta, becomes, let's push that upwards. So we get mv equals little mv plus 2 e gamma over c times v over c. And this formula should be true for arbitrarily small v. Right? It doesn't matter how small v is. This has to be true if momentum conservation is true. OK, this is for v much less than c. Well, what do? You just cancel the v's. OK, so we get m minus m, so we divide by the v. We need it to be non-zero, but any non-zero value. And then we get m minus m times c squared equals 2 e gamma, i.e. the change in mc squared is equal to the energy released in the photons. Okay, so that was the argument. It's very elegant, doesn't really use Lorenz transformations. It just relies on the fact that you can drop things to order v squared over c squared. Other than that, it's very intuitive. Of course, he hasn't really proved the energy equals mc squared. He's just proved that the change in energy, the change in mc squared for a particle, equals the energy it must have given off in radiation. Okay? But it's now quite plausible that imagine the particle completely disappears. I mean, some particles decay, like you take a pion, it decays into 2 photons, and it's gone. So the final mass is 0. And if the final mass is 0, the original mass must have been, the original mc squared must have equaled the energy in the photons. So now it's very plausible that this is true for all particles. So in particular, if m equals 0, e.g. pion going to 2 gamma, then E, the energy released, equals mc squared. And actually, amazingly, in Einstein's 1905 paper, he mentions at the end, maybe this could be checked in radium. Okay? Radium, of course, is a radioactive element. It emits particles, and indeed, the formula, this is correct. What people didn't realize for another 30 years is you could use this to get nuclear energy. Okay? That when one atomic nucleus changes to another by emitting particles, the energy in the emitted particles is exactly equal to the change in the mass times c squared. Right? And that's an awful lot of energy. Right? So I think it's true that the energy in a teaspoon of sugar is enough to blow up Manhattan. Okay? Not that I want to blow up Manhattan. So there's an awful lot of energy in I've messed up this board. Let me, I'll go over there. Okay, so that was Einstein's argument, but you know, so it's very elegant, it's very physical. but we're going to get to a better argument. Before we do that, let us discuss, we're going to discuss particles and their action. Okay, so the world is made of particles and fields. In this picture, we have the F mu nu, but we also have particles like electrons, which carry charges. And I guess the lesson of the last 200 years of physics is that all the physics we know can pretty much be written in terms of an action principle. We don't really know why. The action principle is the best way of representing all the symmetries in a theory, the best way we know of. It's not the only way. You went to David's lecture yesterday. So he was talking about quantum field theories that do not have an action principle. Okay, so far, none of those are relevant to particle physics, as far as we know. And so far, they're only relevant to very special condensed matter systems, where they're very strong quantum entanglement and so on. But it's nevertheless very interesting that there seem to be some physical systems that are hard to describe with an action. But the lesson of 200 years is that the action is the most powerful concept in theoretical physics, and it continues to be incredibly fruitful. So all known physical theories, fundamental physical theories, have an action principle. In particular, we can, and it'll turn out this will help us explain what energy is. The action incorporates all the symmetries. When we put the symmetries into the action, we'll infer there must be energy, there must be momentum, there must be angular momentum, and so on, because of Noether's work. So let's think about a particle. So what is a particle? Well, a particle, of course, is a point in space, but we're going to think about space-time. So I'm just going to draw two of the coordinates, x and ct, and now let's think, what is a particle in that picture? Right, so obviously at every time there must be a point. But the point is allowed to move around in x, and so the particle follows a world line. Okay, so for example, when you came from perimeter from your home country, you followed some trajectory here, presumably less than the speed of light. Okay, speed of light is right angle, is 45 degrees in this picture. So you came along some line, and you came from home, you went to perimeter, you go back to home at some point, and all of us, our lives, we're doing this. Occasionally we meet each other, and so from this point of view, the picture of the world is a picture of space-time and world lines. Okay, so every particle follows a world line, and we'd like to describe the properties of that world line and the properties of the particle in terms of this, what it does on its world line. So how do I describe a world line? Well, I'll use space-time coordinates x mu, and then I'll parameterize the world line with some parameter lambda. Okay, so it might go from minus infinity to infinity. So as this world line goes back into the far past or into the far future, this parameter will run over all of its values, and what we want is x mu. See, what we want are the coordinates x mu. Yeah, we'll get to it. But you, just like we had x prime as a function of x, it needed to be a one-to-one map. we're going to require something of this parameterization. You know, if it's a good parameterization, then the particle world line will be one-to-one with lambda. Pick the bad parameterization, you might have your lambda running up here, and then x mu might go backwards along the world line for a while, and then it might go forward again. That would just be a bad choice of parameterization of the world line. Because the same world line, and now you have two values of lambda corresponding to the same x. So you have to be a little bit careful. So when we say we parameterize the world line, you must be careful that each parameter value corresponds to one space-time point on the world line. Okay, so when we think about this world line, there are, we should try to characterize its properties in a Lorenz invariant way. Okay, so Lorenz invariant properties. Okay, so in particular, we can ask at any particular space-time point which the particle passes through, what's the velocity of that world line? We can obviously form this quantity, dx mu d lambda, which would be the parameter velocity of the world line, and then dx nu d lambda. And this is obviously invariant under Lorenz transformation, because I contracted the indices. The lower indices transform with the inverse lambda, the upper ones with the lambda, so they cancel. So this is equal to eta mu nu dx prime mu dx prime nu under Lorenz transformations. Okay, so whatever coordinate system you use among this class of Lorenz transformed systems, everyone's going to agree on what this quantity is. So if it's, in particular, they're all going to agree if it's less than 0. Everyone will agree that it's negative. The value will be the same for everyone. It'll be negative. If it's negative, we call it time-like. That's for obvious reasons. You see, if I write this out, what I'm getting is something proportional to minus c squared dt squared plus dx squared. So if this quantity is negative, it's telling me there's more, the change in the time outweighs the change in the space, and so it's time-like. And in particular, it's possible to choose a Lorenz frame. If it's time-like, you can always choose a Lorenz frame in which it's only in the time direction. Right? If I take any vector which obeys, it's very plausible. I take any vector where the time component is bigger than the space component, I can do a Lorenz boost to a frame in which the space component is 0, and I only have a time component. If this quantity is 0, we call it null. And that's if the particle is moving at the speed of light. Okay, so that the dx squared, the distance it travels in space, is or mod dx is c dt. So that if it's null, mod dx equals c dt, so it's moving at the speed of light. And that's what photons do. Photons or light waves move at the speed of light, so we call them null. And if it's bigger than 0, we call this space-like. Okay, and this would be a wonderful particle to have, because it would move always faster than the speed of light. Okay, and so far no one's ever seen a particle like that. Except in string theory, where there's a tachyon. A tachyon is a particle that goes faster than the speed of light, but it doesn't exist. And so in string theory, one has to struggle quite a lot to get rid of the tachyons in the theory. And this is called a tachyon. which doesn't exist. Okay, so for some reason, all particles we know are either null or time-like. In fact, you'll find a big literature on tachyons, and people argue that if you could have a tachyon, you could actually travel backwards in time. And then you could kill your parents or do something equally paradoxical. So tachyons don't seem to exist. Though we don't quite know why. Okay, so photons, or wave packets of light are going to be null particles moving at 45 degrees on this diagram. And ordinary particles, massive particles, are going to be time-like trajectories. And so let's focus on those for the moment. So high. Okay, so I'm just stating that, but another way of saying that is if a particle follows a time-like trajectory, it will turn out to be a massive particle. So let me show you that. So to imagine we have some particle which is always time-like. Its world line is always time-like. Then, for such a particle, we can define the proper time. Along the world line as follows. So d tau will equal to dt times, let's write it this way, square root of dt squared minus dx squared over c squared. So obviously the right-hand side is invariant under Lorenz transformations. It has units of time. If I square root it, it has units of time. If the particle world line is always time-like, the argument of the square root is always positive. So I can take the square root. There's no problem. And that's what the change in the proper time is defined this way. Okay, so this is obviously equal to dt square root 1 minus dx dt squared over c squared. And that's, of course, 1 minus v squared over c squared. So v is the velocity of the particle in the frame that I'm using. And so, this is the proper time along the particle world line. Now, when we have this proper time, it's Lorenz invariant. Okay, so we can define all kinds of other quantities. The velocity of the particle. Okay, so we have the 4 coordinates of the particle. That's a Lorenz vector, which transforms under Lorenz transformations. What about the velocity of the particle? Well, now we have a time which is Lorenz invariant. We just have to calculate this, right? And because the d tau is Lorenz invariant and the dx is a Lorenz vector, this is a Lorenz vector. Okay, so this is the 4 velocity. And it'll transform just like any other Lorenz vector. in fact, it follows from this definition that eta mu nu u mu u nu over c squared, it's a dimensionless number, right? And because of the definition of d tau here, this is -1. Okay, let's check that. This is minus d ct squared d tau squared. That's the u naught squared term, and eta 0, 0 is -1, plus dx d tau squared, right? And then if I if I cancel the c squared, yeah, there's a c squared here. And then obviously this is equal to dx squared minus dt squared. I guess I can just put that formula. Well, is it obvious this is equal? If I just substitute this in there, they cancel. Right? Just substitute this in there. And okay, so the four velocity of a particle, the square of it is always -1 for a time-like particle. And we can also obviously take the mass of the particle, but I put an m0 there to indicate the mass in the particle's rest frame. You'll see why later. It's important because this is really a constant. It's just a number. So m0 u mu is the p mu is the form momentum. Just like in non-relativistic physics, p is mu. Well, this is a definition of the form momentum. Where this is the rest mass, which is the same in every frame. Okay, so that also defines a Lorenz 4 vector, which is a form momentum. And then we can interpret this form momentum as E over c as the energy of the particle, and it's 3 momentum. So if you like, I can just define the energy and 3 momentum that way. And then in particular, we find that the energy is P naught C. Sorry, this is P mu. The energy is P naught C, and this is equal to square root of P squared C squared plus m naught squared C to the 4th. Okay, this follows just from the fact that so it follows from this equation. Obviously, eta mu nu p mu p nu is just minus m naught squared, right? If I take this and I use that u squared is -1, then p squared is minus m squared, and now I can use this I can write this as minus e squared over c, e over c squared plus p squared, and solve for e, and I get this formula. So that's the relationship between the energy, defined this way, and the momentum. And the rest mass, of course. And now if I take this formula, so imagine that P so if P squared C squared is much less than m naught squared C to the fourth, then you can expand the square root, and then we get E is approximately, so this is the dominant term. Here we get our mc squared again, m naught c squared, plus 1/2 p squared. So I've got to divide by that and expand. So I'm just going to get p squared over m naught squared plus ... Just expanding the square root in a Taylor series. So this is the same old term. And what is this term? Well, if we go back to here, you see P is m naught u, right? What is u? This is m naught. U is dx dt times dt d tau. Okay, because the spatial components are dx d tau. But the tau we have over there in terms of v. Okay, so dt d tau is that gamma factor. So that's gamma m naught dx dt, which is gamma m naught v. Okay, so you have to be careful that the velocity of the particle is dx dt. It's literally the change in distance over the change in time in the frame you're using, whereas the fall velocity involves d tau. Okay, but if we write this, if v is much less than c, then P is approximately m naught v, right? Because this gamma factor is 1 over root 1 minus v squared over c squared, which is approximately 1 plus 1/2 v squared over c squared plus ... if v is small. So 2 order v cubed in this case. This formula is correct. Okay, so given that formula, this becomes 1/2 m naught v squared. So what you see from this is just recover the usual formulae of classical mechanics, that the momentum is mv, the energy is 1/2 mv squared, but in addition, you have this funny extra term, m naught c squared. Okay, so again, it's pointing to the E equals mc squared. This doesn't really prove E equals mc squared at all, but it certainly says it's sitting there in the formalism. This is just a constant, so I can just ignore this. But it's definitely sitting there in the formalism. And I will show you now that E equals mc squared really is the energy of the rest mass. Okay, so let us now describe the action of a particle. Let's bring this one down. Okay, so as I mentioned, the fundamental formulation of the laws of physics for the last 200 years has converged onto an action principle for very, very profound and interesting reasons which we do not understand. But I believe they strongly relate to relativity, and there's a little mathematical trick I can explain to you at the end of the lecture, if you like. The connection between action principles and relativity and quantum mechanics. But I don't want to distract you now. Let's just say we want to derive the action for a relativistic particle. So what's the point about the action? Well, the point of the action is a variational principle, some function of the dynamical trajectory, whose variation being 0 gives the equations of motion. Okay, so that's the idea of an action. Now, if the equations of motion have some symmetry, the easiest way to ensure they have some symmetry is just to build the symmetry into the action. Right? To make sure the action is the same for all trajectories related by the symmetry. If it's the same, then the equations of motion are going to be the same. Okay, so this is the best way. S is the, or making S invariant under some symmetry is the best way we know to ensure that the equations of motion are also are invariant under that symmetry. Okay, so the symmetry here will be the Lorenz transformations, and of course translations as well, but the more tricky ones are the Lorenz transformations, the x prime going to lambda of x. So I've got to write down some action. I've already told you what the dynamical trajectories are, x mu of lambda. Okay? If I know that x mu of lambda, that's the trajectory of the particle. So what action can I write down which is invariant under Lorenz transformations? It's basically only one. Should be some quantity that depends. I can tell you, let's imagine the trajectory begins at x0 mu and ends at x1 mu, right? And then the variational principle says consider all possible paths from here to there. And the equations of motion are the ones for which the action, the variation of the action is 0 on that path. Okay? So it's like finding an extremum of some function. That the classical trajectories extremize this function on the space of paths. So what can I write down for a path? I mean, here it is. What's the property of that path? What's a natural property of that path? I mean, I'll write some other paths, okay? So we've got to keep the 2 points fixed. I could consider a path like that, a path like that, a path like this. I can do a straight line. I can even do one which goes backwards in time. What do I want? What's the property of those paths? Pardon? No, I want a quantity. Time-like is a quality. I want a quantity which depends on the path.
Arc length?
Arc length is good. As soon as I say length, how am I going to measure the length?
Space-time coordinates.
Yes. And how do I measure length? So I take a little piece of the arc, and what's the length of this in space-time? It's just this eta thing, right? Eta mu nu, dx mu, dx nu. Right? So if dx mu is this little 4 vector from the one point to the other, then this quantity is Lorenz invariant. So providing I build my action out of that quantity, it's going to be Lorenz invariant. So let me try this. I've got to parameterize my path. That plays the role, if you like, of the time along the particle path. Right? It's living in space-time, but there's a parameter which tells me where I am in space-time. So I could try writing this down, eta mu nu dx mu d lambda dx nu d lambda. Okay, so, and we could choose lambda to go from some initial value to some final value. Is that a good expression? It's Lorenz invariant, so that's good, providing lambda doesn't change when we do Lorenz transformations. That's Lorenz invariant. But it has a sort of nasty property. Can you see what it is? You see, this parameterization of the line shouldn't really matter, right? Any function which varies monotonically, so if I have one lambda, let's imagine I have some lambda which goes from a small value to a large value. If I pick some other lambda, which is a function of this lambda, but it's monotonic, okay, so it does something like that, it's equally good, right? Why not? So for each lambda, there's a single value of lambda tittle, and therefore there would be a single point on the world line. Okay, so providing you reparameterize the line in any way which is monotonic, nothing really changes. There's no preferred lambda. Okay, so the unfortunate thing here is that the powers of d lambda don't match. Okay, so if I write this as d lambda twiddle, eta mu nu dx mu d lambda twiddle, this would be another parameterization, right? And this is not equal, because the d lambdas come in different powers. So that's a bad thing. If your action depends on how you parameterize the line, it's a bit ridiculous. So what do I do to correct that fact? Square root. Okay, so that makes equal powers of d lambda, and in fact, you can just cancel them, right? And then if I know the particle is a time-like world line, actually I should put a minus sign in here, because for time-like world lines, that quantity would be positive and the square root is well defined. Okay, so this is a good action. This is nothing but d tau. So the action for the natural action for a world line is just integral d tau. What could be easier? Okay, so let's put the lambda back, because we're going to imagine there's some lambda. This is still d tau. Good, so that's the action for a point particle. And actually, it's going to turn out, I mean, I can put any constant I like in front of it, and it will turn out that the natural constant to use is minus m naught c. So, but for the moment, just think of this as some constant. The overall constant in an action doesn't affect the equations of motion at all, right? Because it doesn't affect delta S equals 0. But when we get to Noether's theorem, we'll find the definition of the energy depends on this constant. Okay, so for the moment, just imagine there's some constant there, and take my word for it that it'll turn out to be m naught c. Now, what we're going to do is, of course, vary the action to get the equations of motion. Okay? But I want to impress you with how powerful this action is, not just by doing the free particle. Free particle is kind of trivial. I vary the action, I'm going to get d2x d tau squared is 0, x is linear in tau, it's a straight line. You know, no prizes for deriving a straight line. So free particle is very boring. Its equation of motion is just d2x mu d tau squared is 0, and the solution is x is linear in lambda, which is a straight line. let's do something a little bit more interesting. Let's imagine that our particle couples to electromagnetism, has a charge. It's an electrically charged particle, right? So the question is, how am I going to couple? This is the free particle action. But now I want to add the coupling to electromagnetic fields. Okay, so I'm claiming that the action is the perfect way to do this. How can I couple this world line to electromagnetic fields? I need to put something in the action. What can I put? Well, the electromagnetic fields, I could try F mu nu, right? And then maybe that would say, all right, well, let's put dx mu d lambda dx nu d lambda. Is that a good idea? What's wrong with that? What's wrong? What's wrong with that expression? Something very bad. This can't be an action.
It's anti-symmetric.
Very good. That's anti-symmetric, that's symmetric, so this is just identically zero, so no chance. Okay. So that's hopeless. So what else can we do? We can't couple F to dx d lambda. Doesn't work.
You can use A.
We can use A. Brilliant. So let's use A. Okay? And what can we couple A to make a Lorenz invariant? There's only one thing, right? dx d lambda. That's it. So that is a particle coupled to electromagnetic field. And the action is just the simplest thing you could imagine. So what I'm supposed to do is integrate along the world line, work out the vector potential on the world line. Okay, so I work it out at the spacetime point where the particle is, and then I multiply by the velocity of the particle, and that is. Okay, so that is the obvious thing to write down that couples a particle to an electromagnetic field, and it is more or less unique. Okay? And when I say more or less, you could muck around with other things. Can you think of something else I could include here if I wanted to? If I wanted to complicate the action, what would I do? Is there anything? So imagine I want to put something here. I don't want to be simple. I want to be complicated. What could I put there?
F mu nu, F mu nu.
Yeah, very good. Okay, so we could just put this. It's also a function of x of lambda. I could stick it in there, and there's no reason for it to be there, but I could put it there. And I can use higher powers of f, and there are many other things I could do. So, but this is certainly the simplest action you could write down. And so let's try that. Right. What do you do with an action principle? You vary it, and you see what the equations of motion are. So when you vary this action principle, I claim you will get the equation of motion of the particle. And what is that? What equation are we trying to derive? Particle in electric and magnetic fields. What equation does it obey? M d2x dt squared equals q times what? Electric field, have you seen that equation? Plus something else? B cross B. Right, this is the Lorenz force. Same old Lorenz, by the way. Okay, so We're trying to get to that equation. That's the equation describing the motion of a charged particle in an electric and magnetic field. And what I claim is that this action gives exactly that equation and nothing else. So I hope this convinces you that relativity is pretty damn good. Okay? Because essentially in relativity you don't have to remember anything. Right? Except electromagnetic fields, what are they? Well, they're antisymmetric tensor. Right? What's a particle? Well, it's a world line. How do I couple a world line to a particle? Well, f mu nu is derivative of A, so let's couple it with A. That's it. Right? You'll never have to remember any formulae ever again about electrodynamics. It all follows from this. Okay, so let's vary it. This is a bit of a pain. And so, do you want to do it before the break or after the break? It's about 3 lines of algebra. I'll leave it to you. All those to do it now?
3 lines, that's it?
Yeah. Piece of cake. Actually, there's a great quote from Einstein in that book I mentioned, The Road to Relativity. So he's working on general relativity, and they'd already worked out all this stuff. So he's working on general relativity and trying to build gravity in, and he said, I've suddenly realized how important mathematics is. And he says, compared to what I'm trying to do now, special relativity was child's play. Okay. So all of this is child's play, right? But we'll be done with it this week, and then next week we'll grow up. You try. Maybe we'll be teenagers next week. Okay. All right, let's try the child's play. I'm going to put these up. Okay, so let's vary it. So what do we mean by varying it? We mean that x mu of lambda goes to x mu of lambda plus some variation, delta x mu of lambda. And this is supposed to be small. And so that we will just work to first order in the variation. Okay, because to find an extremum, you just need to differentiate something near a point, and that just means working in the vicinity of the final extremal path that we want. So let's vary the first term. As I said, it's a little bit of a pain. I'm going to, for simplicity, I'm going to ignore the d lambda. Okay? Obviously, the d lambda cancels. And so I could write out the d lambda in every term, but I'm just going to not. All right? So you can put it back in if you like. And so the variation of the action is integral m naught c e to mu. So I've got to vary that square root. So when you vary a square root, what you get is the variation of the argument divided by the square root times a factor of a half. Okay? So a half. But you see, when I vary the argument, it's a square. So I'm getting a factor of 2. So let me just write down the answer. This is, so we have minus m naught c. And then from varying the argument, I get another minus, which cancels the first minus. And then I get eta mu nu dx mu d delta x mu. That's in the numerator. And as I said, I'm just forgetting the d lambdas, because they always cancel anyway. Okay, so if you want to interpret what the hell does this mean, d of delta x mu, it means the d by d lambda of delta x mu. Okay? It's the derivative of the variation of the path. But as I said, just for the algebra, I'm going to remove the d lambdas. Now I've got to divide by the square root. So I divide by square root of minus eta mu nu dx mu dx nu. But of course, what is this? This is just the tau. All right, so this whole thing here is, and there was a, yeah, so the whole thing here will turn out to be d tau, and then m naught, actually this is not tau, this is c d tau. Trying to be careful with my c's. So this is m naught times eta mu nu dx mu d tau d delta x mu d tau. Okay, the square root here is c d tau. Let's try and write this in a more d by d tau of delta x mu. C's cancelled. There was a c here. Okay. Yeah, I'm being careful with the c's for special relativity. When we get to general, I'm just going to set c equals 1 and forget about it. You can always choose units in which the speed of light is 1 and forget about it. But it's kind of helpful in special relativity. For example, it's not really obvious that when you work out this expansion of the energy, the c's are going to cancel. They cancel in this term. It's kind of telling you that classical mechanics makes sense when you forget about c. But you've got to subtract off this term in order to have answers which are independent of c. So it's useful to keep track of c as a sort of formal device. The limit of classical mechanics is when v is much less than c. But it may be all the formalism you use will generate terms which are constants, which are multiples of c, and you have to subtract all those off. Okay, so this is the first part of the action. Now the interesting part is, of course, the variation of this guy. Now let me see. I think I wrote it incorrectly. Sorry. I don't want the m naught c multiplying this thing. It should be just this. And this should be here. Okay, this is the extra term. In fact, you could have told that just from dimensions. Okay. I think I already discussed scaling. Remember, if we scale coordinates, we argued you get the inverse square law just from dimensions. And scaling symmetry. So likewise, this action should be invariant well, it should be, the action should be dimensionless in terms of lengths and times. And you can sort of see that f, if you remember, f goes like, if x goes like lambda, f goes like lambda minus 2. That's the inverse square law. A goes like 1 over lambda, because f is derivative of lambda. So you see here, this goes like 1 over length, this goes like length, and so this is dimensionless, because q is dimensionless. Here, the square root, this d tau is c d tau is a length. Okay, so I need something to cancel the dimensions of length, and essentially the mass is what cancels the length. So in other words, you need a dimension full constant here, but a dimension less constant here. Okay, so let's continue varying. So I've got to vary this guy, right? So Sorry. Sorry, I'm just suffering a brain freeze. Try and proceed. So what I get is plus Q yes. Okay, so what I get is plus. Now I've got to vary the a mu. So how do I vary a mu? You differentiate it with respect to the argument and then vary the argument. Okay, so just use the chain rule again. So I get d nu a mu times delta x nu. Okay, that's the variation. This thing is delta of a mu of x. Right, so I differentiate it with respect to each argument, and then I multiply by the variation in the argument. Okay? So that's the first term, and this one is multiplied by dx mu d tau. Notice that this is d lambda. I could write this as d tau. Doesn't really make any difference because it cancels here. So this part of the action is actually very nice anyway. It's invariant under reparameterizations already. No need for a square root or anything like that. And the d lambda I can just replace with a d tau, providing they're in one-to-one correspondence. Okay, so the second part of the variation, I've got to vary this guy. So I write plus q a mu d by d tau delta x mu d tau. Sorry? I've got to vary this guy, right? This is a function of lambda. So the x goes to x mu plus delta x mu, and I just keep the delta x mu. So that's the variation. Okay? And I'm because I learnt from this term I should introduce the d tau. I'm going to replace the d lambda with d tau here. There's no I don't lose anything by doing that. Now, when you do variational principle, is what always happens. You get derivatives of the trajectory. And what do I do to remove this term? Integrate by parts, right? We always do that. So if I integrate by parts, I'm going to have to integrate by parts here. I want everything to be multiplied by delta x nu. Then I'm going to say delta s equals 0 for all delta x mu, and therefore the coefficient must vanish. Okay, so we're going to have to integrate by parts. Let's do this one first. So this one gives us minus m naught d2 dx d2 d tau squared x mu delta x mu. I'm just using the eta to lower its index. This term I can leave as it is. D mu a nu. Sorry, d nu a mu. But this term I'm going to integrate by parts. Okay, so I'll integrate by parts and then I'll combine these two terms. So integrate this one by parts, I get minus d by q, d by d tau of a mu, delta x mu. Differentiating a mu, I get del nu a mu dx nu d tau. Just the chain rule again. Differentiate a with respect to its argument, which is x of tau, and then differentiating the argument with respect to tau. Okay, so this term, let's see. So I'll just put it all together. So I get this times delta x mu. Okay. Sorry?
We skipped the middle one?
The middle one went there. I haven't quite finished with the middle one. Okay. I'm going to combine it with this term. You see, I've got, in this middle one, I've got d nu a mu with delta x nu dx mu d tau. In the last term, I've got delta x mu with dx nu d tau. So these indices got flipped between the two terms. So what I do is just relabel these indices, called nu mu and nu, and mu that way. Okay? And then what I've got here is minus d mu a nu, and then delta x nu dx mu d tau. Okay, so now everything is multiplying. Well, let's relabel this one as nu. And now everything is multiplying delta x nu. In fact, what I want to do is lower that and raise that. Everything multiplying delta x nu, and so we can just write down the coefficient. So delta s equals integral d tau. The first term gives me, and then I'll put my delta x nu here. First term gives me minus m naught d2x nu d tau squared. Why did I put a minus there? Shouldn't be a minus, should there? No, there is. I'm sorry, integrated by parts. Yeah, there's a minus. And then I have this other term, q, d nu a mu minus d mu a nu, dx mu d tau. Okay? So this equals 0 for all delta x nu. So it follows that m naught d2x mu d tau squared equals q equals q f nu mu dx mu d tau. Sorry, that should have been a mu, shouldn't it? Okay, voila. So this is the Lorenz force law. Okay, why? Because when I look at the spatial indexes here, if nu is I, I'm going to get something like MA, and Fi0 is the electric field, but dt d tau is nearly 1 if the velocity is small. Okay? If the velocity is small, dt and d tau are nearly the same. So this is going to give me E from the Fi0 term. And from the Fij term, dxj d tau, it's going to give me exactly epsilon ijk bj vk. So it'll give the Lorenz force term. So you can check that this gives exactly the right equation of motion. Again, there were hints of this in the Lorenz force law. Now, if you say the Lorenz force law doesn't look very relativistic, right? How do I combine it? Well, you do it in the completely obvious way. You want to make a four vector out of the E and B and dx dt, you write that down. That's all you can do. Okay, so I think we'll come back at 1:45. We'll aim for 1:45 and we'll see how it goes. All right, have a good break. Yes, go ahead.
I'm just, I'm kind of confused.
No, just say exactly where.
I don't know.
So, okay, so let's go through it again. We'll start off with a mu dx mu d lambda.
Okay.
So a mu is a function of x.
Right.
Okay, so what do I have to do? I have to write the whole thing as a function of x plus delta x. So this is d by d lambda of x plus delta x. And then keep everything linear in delta x. That's all I care about. So I'm going to subtract off the 0th order term and then just keep the linear terms. So this is going to give me delta x alpha d alpha a mu. That's what this one is, right? Because I just do a Taylor series in delta x around a mu of x. Right? So I'm just saying that a function of x plus delta x equals the function of x plus delta x times d by dx of the function of x. That's all we're doing, just Taylor expansion. But the thing is I'm varying delta x0, delta x1, delta x2, delta x3. So I have to have all those terms in there. Okay? So this is just keeping the variation in. So yes, so I get the first variation of A, gives me this one. And then that would multiply the 0th order guy from here, the dx d lambda. Okay, so that's where I called it nu. That's where the first term came from. First term came from varying the A. The second term came from this piece. Right, so I get plus, I can now keep A to 0th order, but I've got to keep the first order correction to this piece. So d by d lambda of delta x mu. So then I took this term and I integrated by parts. So this became minus d by d lambda of that.
Isn't there usually two parts when you integrate that parts from the other part?
Surface term. Ignore the surface terms. When you vary actions, that's what you always do. The statement is that when you vary an action, you get, just think about classical mechanics, right? We do half m x dot squared minus v of x. How do I get the equation of motion? I vary it. I get m times x dot delta x dot minus dv dx delta x. So I've got to get rid of this delta x dot. The only way I can do it is by integrating by parts. So I get minus mx double dot times delta x, and I ignore the surface terms. And then I say this must be true for all delta x.
Why is that okay to ignore them?
You don't really ignore them. When you think about it more carefully, what you're saying is you fix the initial and final points, and then you consider all variations which vanish at the initial and the final point. So what you're really saying is consider all variations delta x of lambda which are 0 at lambda 0 and lambda 1. Okay, so then when you vary integrate by parts, you always get something involving delta x, the variation at the endpoints. And you just, by definition, you say, I don't care about variations of the endpoints. I only want the action to be stationary under any variation which vanishes at the endpoint.